Hi, I'm Björn, and I'm investigating how to use evolutionary computation to discover new kinds of sounds, hopefully, at least strange sounds. And I kind of like viewing this as an alternative approach to how large models today commonly re-synthesize their training data, where instead the evolutionary processes start from scratch and gradually complexify. So the focus is more on diversity of discoveries rather than matching existing sounds. And my initial investigations into this involved interactive evolutionary computation, where the human participant is asked to select the most interesting parents for the next generation, and so on. And this was modeled on previous experiments in the visual domain, where people selected pictures. But the temporal dimension of sound requires more effort to evaluate each individual. You get tired more quickly, especially at the beginning when listening to maybe noisy sounds and so on. But I even tried to implement other hacks to lessen the fatigue that you get by allowing you to branch off other people's experiments. So that was also modeled by this previous visual domain experiment called Pick Breeder. But I guess, well, still there was this temporal problem and there weren't really any people except me. So that effect wasn't really kicking in. So that led me to focus on automating the discovery process. And for that, I've been fascinated by the field of quality diversity search. Some of you may know novelty search, for example. That's an algorithm from that family. And so this emphasizes a diversity of discoveries in favor of strictly optimizing towards specific goals. And through that, you can collect stepping stones and often through unlikely paths, which may lead to optimal solutions or even transformational discoveries. And so initially, when investigating this approach for discovering sounds, also in this case, being inspired by the visual domain, I tried defining the search space and quality evaluation with a supervised model, a pre-trained classifier like YAMNet. And here you can see some results of the scores in each class throughout the generations. And the results have been interesting, and we've observed the so-called goal switching happening quite quickly or frequently, which is a measure of how often new elites in one class are children of elites in other classes. So this is one measure of how the algorithm is collecting stepping stones throughout the search space. And in this case of supervised classification, we can even see traversals between contexts or groups of classes. So non-musical and musical contexts, which is a kind of a nice demonstration of how important it can be to have a diversity of discoveries. So you can have a parent from a non-musical class for a musical sound, for example. But I also tried methods for autonomously defining the search space with unsupervised models. But there I faced more choices. So here on the left, there's a supervised model, quite simple and everything neatly packaged in a single classifier. But when traversing into the unsupervised field, I faced more choices. So I had to consider what models to use to define the search space, for example, PCA versus an autoencoder, what features to extract from the sounds and to use to project into those spaces, and what defines the quality or interestingness of the sounds. And that's maybe the hardest question. So I tried quite a few combinations of these, where we can at least say that each has their own characteristic, rather than one being clearly more successful than the other. And here we can, for example, see examples from reference-based and reference-free evaluation methods, where in the case of referenced evaluation, it is computed as distances to entries in a vector database. And the reference-free evaluation is implemented by detecting problems in the audio signal. And a bit on the audio synthesis approach. So for defining the genomes and synthesizing the sounds, I've been using this homegrown synthesis approach, which is based on the coupling of compositional pattern producing networks, or CPPNs, with DSP graphs, or basically synthesizer patches. And those CPPNs can have different activation functions at each node, and they were initially proposed as an efficient developmental encoding for unfolding development during evolutionary processes. And the idea is that this could also be interesting for unfolding timbral development. So here you can think of each CPPN on the left as an oscillator, but instead of producing a steady signal, it produces many patterns and sub-patterns, which can unfold over any temporal dimension, or any temporal duration, basically. And currently I use those signals as sources for control and audio into the synthesizer patch. So the same network can be producing an audio here and some, for example, control of a filter frequency and so on. And I also, initially I had a single CPPN network, but then one intuition was that it was maybe too demanding for a single network. So later I have explored having specialized network for different frequency ranges. So each network is basically simpler. Yeah, and this has been compared with DDSP in a way, which I haven't investigated, but I would love to. And one idea is whether it would make sense to couple this with these CPPNs with DDSP. So we would have CPPN plus DDSP as a synthesis approach. But then in any case, it would be interesting to try other synthesizers basically in this evolutionary loop, which I haven't yet really. But this combination of CPPNs and DSPs, they offer a vast range of possibilities to explore. And you could argue that there is a lack of so-called inductive bias in this setup or opinions. But still the evolutionary loop and the selection pressure has been able to come up with interesting discoveries. But in the case of unsupervised approaches, I've been observing a bit more noise than when using supervised models. And maybe you'll hear some of this in the demo later today. But of course, yeah, we want to hear the sounds that those experiments are coming up with. And I've tried several approaches. The first one was to simply render the genomes into files and listening to random samples. And then I created this command line utility to automate the playback, so I could sit back and listen, hands-free. And then I implemented this web interface where you can slide through the experiments, their classes, and their generations. And for each sound, you can vary the duration, the pitch, and the velocity. So in a way, explore this along 6 dimensions. But I had the most fun throwing those pre-rendered sounds into this application called AudioSteller, which then arranges them in 2D according to their sonic relationships. And I set up some automated sequencing through this and even live streamed it. You can still listen to that on YouTube. So that was nice, but I also wanted to explore the sounds according to their phylogenetic relationships, because these are indeed results from evolutionary simulations. So I developed this interface where the evolved trees and the search space representations can be explored both visually and sonically by hovering the mouse over the notes. And I've also added some compositional capabilities, heavily inspired by AudioStellar, which I place here in the background. So you can see that the interfaces are quite similar, but one is a native desktop application, but this is a website, basically. So where you can instantiate different sequencing units to kind of see how the sounds work in a compositional setting, but here more according to their phylogenetic or family relationships, basically. And I'll be demoing this hopefully later today, but maybe you should listen to a bit of interaction in this interface. Here I'm kind of happy how snappy the playback is after I incorporated the elementary of the library into it for the sequencing. Yeah, I didn't want it to adjust it. So now it's playing automatically. And here I'll get another type of unit with the loop each sound. And sound starts relatively fine when you cover the notes. In a way, you can create a polyribbon. Here I'm trying out a way of synchronizing it. They start in. And you can play with this at this website, so it's back online. It is mainly optimized for the desktop, but I added this icon here to demonstrate that it actually does, in a way, work on your phone, even though it's not optimal for touch interaction yet, at least. So it can be interesting to interact with those sounds from past evolutionary processes, but those are kind of like fossils. The evolution already took place, and you can take a look at the results. But going forward, I'm interested in establishing something closer to the continuous open-ended evolution in nature. So the project started with fully hands-on interactive evolution. Then I've explored mostly hands-off automated evolution running on large computing clusters. But the most interesting environment probably lies somewhere in between. But then there's the question, where in between is it most interesting to stay? So could it be fun to throw your opinions into a common genome pool and see how those align with others? Or would it be nice to see some of your sound discoveries becoming ancestors of other interesting discoveries, perhaps whole lineages? And for the sounds that you do find interesting, how would you like to use them? Would you like to use them as a sound map in your favorite DAW or somewhere else? So it would be great to hear your thoughts on that and anything else. Thank you.